I have a dream that one day
Hi there everyone, welcome to the second lesson on Surds. In the previous lesson, we mentioned that there are 5 standard techniques that we want to discuss for Surds. These are simplifying expressions, rationalizing the denominator, proving identities, the order of magnitude, and solving equations. In this lesson, we want to look at the first standard technique, namely simplifying expressions. In example 1 it says, simplify each of the following without the use of a calculator, and we are given these 4 expressions. Let's look at the first one. So we have the square root of 18 plus the square root of 32 minus the square root of 72. Now, the largest perfect square that goes into 18 is 9. So we have the square root of 9 times 2. Then the largest perfect square that goes into 32 is 16, and it goes twice. So we have 16 times 2. And then the largest perfect square into 72 is 36. So we can write 72 as 36 times 2. Now we use the rule of Surds that says the root of a times b, or the square root of a times b, equals the square root of a times the square root of b. So then applying this rule, we get the square root of 9 times the square root of 2 plus the square root of 16 times the square root of 2 minus the square root of 36 times the square root of 2. The square root of 9, of course, is 3, so it's 3 root 2. Then we have 4 times root 2. And the square root of 36 is 6, so it's 6 times square root 2. Note that these are all like terms. 3 plus 4 is 7, minus 6 is 1. So we're left with 1 root 2, or just root 2. Let's look at the second expression here. So we have the square root of 45, minus the square root of 80, all over the square root of 125 minus the square root of 5. Now, the largest perfect square that can go into 45 is 9, and it goes 5 times. So we can write the square root of 9 times 5. The largest perfect square into 80 is 16, and it goes 5 times. Into 125, the largest perfect square is 25, and it goes 5 times. Now we're going to use the rule of Surds that says the square root of a times b equals the square root of a times the square root of b. So applying this rule, we can write a numerator, or the first term in the numerator, as square root 9 times square root 5, and the second term as square root 16 times square root 5. Then in the denominator, we can write the square root of 25 times the square root of 5. The square root of 9, of course, is 3. So we have 3 square root 5 in the numerator as the first term. And here we have 4 times the square root of 5. Then in the denominator, we have 5 times the square root of 5 minus the square root of 5. In both the numerator and the denominator, we now have like terms. So 3 minus 4 is minus 1. So we're left with negative the square root of 5 in the numerator. And 5 minus 1 is 4. So we have 4 square root 5 left in the denominator. Then these cancel. And we're left with negative 1 over 4. Let's go to number 3. So we have 2 over the square root of 5 plus 2 minus 2 over 2 minus the square root of 5. And this is all to the negative 2. Now, we're going to write the fractions inside the brackets as one fraction. But before we do that, we're going to do a bit of manipulation. I'm going to rewrite the denominator in the second fraction inside the brackets. I'm going to switch around the terms. So we're going to write the square root of 5 minus 2. But then the sign in front of the fraction will change to a plus. So essentially we've taken out a negative from the denominator of the second term. Now we can find the LCD. We want to write these two fractions as one fraction. So the LCD is square root 5 plus 2 times square root 5 minus 2. Now you can see why we switched around these terms, because we get a difference of squares in the denominator. Now, root 5 plus 2 into the denominator, what is left is root 5 minus 2 multiplied by the numerator, then plus root 5 minus 2 into the denominator, we're left with root 5 plus 2, once again times the numerator, we can simplify the numerator. So we're going to multiply out. We leave the LCD as is at this stage. So multiplying the 2 inside the brackets here, we get 2 root 5 minus 4. And here we get 2 root 5 plus 4, this is all to the negative 2. So now we can add like terms in the numerator. Of course, the 4's will cancel, and 2 root 5 plus 2 root 5 is 4 root 5. We can also multiply out the factors in the denominator. It's going to be a difference of squares. So squaring the first term, the square root of 5 squared is 5, minus, then squaring the second term, we get 4. So we essentially left with the square root of 5 times 4 over 1 all to the negative 2. Now we can use a law of exponents and we can invert the fraction. We can write it as 1 over 4 root 5 and the power becomes positive. So positive 2. Then 1 squared is 1, 4 squared is 16, and root 5 squared is 5. And this, of course, is 1 over 80. So then, this expression simplifies to 1 over 80. Let's look at the last expression here. We're going to start by applying BODMAS again and simplify inside each of the two brackets. So, of course, the square root of 8 we can write as the square root of 4 times 2. The highest perfect square or largest perfect square that goes into 8 is 4. And we can write this as square root 4 times square root 2, which of course is twice the square root of 2. So we have twice the square root of 2 divided by 2. Earlier on we saw that 18 we can write as 9 times 2. So the square root of 9 being 3, we can write the square root of 18 as 3 times the square root of 2. And 72 we saw that we could write as 36 times 2. And the square root of 36 is 6. So it's 6 square root 2. Then in the second set of brackets, we have 2 over square root 2. And once again, we can write the square root of 8 as 2 square root 2. And this is to the negative 1. We continue simplifying inside the brackets. The 2's cancel here. So we're left with square root 2 minus 3 times the square root of 2 plus 6 times the square root of 2. In the second set of brackets, we can write the two fractions as 1 using the LCD. And the LCD in this case is 2 square root 2. So square root 2 into the LCD, 2 remains, times the numerator is 4. 2 root 2 into 2 root 2 once, times 4 is 4. In the first set of brackets, we have like terms. So 1 minus 3 is minus 2, plus 6 is 4. So we have 4 square root 2. In the second set of brackets, 4 plus 4 is 8. So it's 8 over 2 root 2. Of course, 2 can go into 8 4 times. So it's 4 square root 2. Here we are left with 4 over root 2. Now, because the power is negative, we can invert the fraction and the power becomes positive 1. So root 2 basically over 4. Then these 4's will cancel and we're left with square root 2 times square root 2, of course, is 2. Let's look at your answers to this question. So here's the first one. We can start by simplifying inside the brackets. The largest perfect square into 48 is 16, and it goes thrice. So we can write 48 as 16 times 3 under the square root. Then the largest perfect square into 75 is 25, and it goes thrice. Into 108, it's 36, and it also goes thrice. Now we can use the law of surds that says the square root of AB equals the square root of A times the square root of B. So the square root of 16 times 3, using this law, is the square root of 16 times the square root of 3. And here we have the square root of 25 times the square root of 3, and the square root of 36 times the square root of 3. The square root of 16, of course, is 4. Of 25 is 5. And of 36 is 6. We can simplify further inside the brackets. 3 times 5 is 15. And 2 times 6 is 12. Now we have like terms inside the brackets. 4 minus 15 is minus 11, plus 12 is 1. So we have the square root of 3 left inside the brackets. And lastly, the square root of 3 times the square root of 3 is 3. And here we're using this law, the square root of A times the square root of A being equal to A. Let's look at the second expression. The largest perfect square into 72 is 36, and it goes twice. Into 18 is 9, and it also goes twice. We can split up the first term in the numerator as the square root of 36 times the square root of 2, and the first term in the denominator as the square root of 9 times the square root of 2. Then the square root of 36 is 6, and the square root of 9 is 3. So we have like terms in both the numerator and the denominator. 6 minus 1 is 5. So we have 5 square root 2 in the numerator. And 3 minus 1 is 2. So 2 square root 2 in the denominator. And these cancel. And we are left with 5 over 2. So 5 over 2. Let's look at the third expression. Once again, we start by simplifying inside the brackets. And we can write these two fractions as one fraction. The LCD here is the square root of 3 plus 1 times the square root of, or rather times 1 minus the square root of 3. Now, the square root of 3 plus 1 into the LCD, we are left with 1 minus the square root of 3, and we multiply it by the numerator. Then 1 minus the square root of 3 into the LCD, we are left with the square root of 3 plus 1, and multiply it by the numerator as well. We can multiply out the numerator, so 5 into the brackets here, as well as into the second set of brackets. in the LCD, or in the denominator, we have a difference of squares, because we can write the denominator as 1 plus square root 3 times 1 minus square root 3. So we square the first term, so that's 1 minus, and we square the second term. We know that there's a rule of Surds that says the square root of a all squared is equal to a. So the square root of 3 squared is 3. So we have 1 minus 3 in the denominator. So these terms cancel in the numerator, and 5 plus 5, of course, is 10. And in the denominator, 1 minus 3 is negative 2. And inside the brackets, it simplifies to negative 5. We have a negative power here, so we can invert negative 5 and the power becomes positive. So it's 1 over negative 5. And it's all to the positive 3. So here we're using the exponential law. A over b to the negative m is b over a to the positive m. Note that the negative inside the brackets doesn't change. Now, a negative cubed is negative because 3 is an odd number. So we have an odd numbered power. And then 1 cubed is 1, and 5 cubed is 125. Let's look at number 4 here. We have a choice as to how we want to proceed. We can either square out each set of brackets, or we can regard this as a difference of squares. I'm going to go with the second option. Remember that x squared minus y squared is x minus y times x plus y. So we can regard this, the first term in the expression, as x squared, and the second term as y squared. So we have x squared minus y squared. Then applying the difference of squares, we can take the square root of the first term, which is just 5 root 2 minus root 3. So that's a square root of the first term, in other words x, minus the square root of the second term. But we have a minus here, so we're going to need brackets. So this is a square root of 2 minus 5 times the square root of 3. So we have x minus y. And now we need x plus y. So 5 root 2 minus root 3 being x, plus the square root of 2 minus 5 times the square root of 3 being y. So we have x minus y, so x minus y, and then x plus y. We can simplify further inside each set of square brackets, so it's 5 root 2 minus root 3. We can multiply the minus into the brackets here. And we can add like terms in the second set of square brackets. 5 root 2 plus root 2 is 6 root 2. Minus root 3 minus 5 root 3 is minus 6 root 3. We can also add like terms in the first set of brackets or square brackets. 5 root 2 minus root 2 is 4 root 2, and minus 1 root 3 plus 5 root 3 is plus 4 root 3. We can take out 4 as a common factor here. So 4 into root 2 plus root 3. And we can take out 6 here as a common factor. We actually need a 6 here. So 6 into root 2 minus root 3. 4 times 6 is 24. And we now have a difference of squares in the two sets of square brackets. So we square the first term. The square root of 2 squared is 2. Minus, we square the second term. And the square root of 3 squared is 3. And of course, 2 minus 3 is negative 1. And 24 times negative 1 is negative 24. Coming to number 5. Six to the n, we're going to rewrite using prime factors as 3 times 2 all to the n. And using the laws of exponents, we know this is 3 to the n times 2 to the n. So 3 to the n times 2 to the n. We can split up the term 3 to the n plus 2 into 3 to the n times 3 squared. And of course here we're using the exponential law, a to the m plus n is a to the m times a to the n. So this is all over 2 to the n plus 9. So the nth root. We can take out 3 to the n as a common factor in the numerator under the square root. And we're left with 2 to the n plus 3 squared, which is 9. These cancel, and we are left with the nth root of 3 to the n. Now we're going to use the law that says the nth root of a to the m is a to the m over n. So this equals 3 to the n over n. And n divided by n is 1. So it's 3 to the 1, or just 3. Let's look at number 6. There's several ways in which you can proceed here. I'm going to start by splitting up the 48 and the x to the 6 here. So it's a square root of 48 times the square root of x to the 6. Now the square root of x to the 6, the square root of x to the 6 is x to the 6 over 2, which is x cubed. So we have x cubed, and splitting up the 27 and the x to the 6, it's a square root of 27 times x cubed by the same principle here. So in the denominator, we have 2 times 3 to the half, and the fourth root of x to the 8 is x to the 8 over 4, in other words, x squared. So the largest perfect square into 48 is 16, so we can write the square root of 48 as a square root of 16 times 3. And 27, the largest perfect square into 27 is 9. So we can write the square root of 27 as a square root of 9 times 3. Now, the square root of 16 is 4, so we have 4 square root 3 x cubed, and the square root of 9 is 3, so we have 3 square root 3 x cubed. So we have like terms in the numerator. Four minus 3 is 1. So we're left only with 1 times the square root of 3 x cubed in the numerator. And this is 2 times. And 3 to the half I can write as a square root of 3 as well. Then these factors will cancel, and x squared into x cubed x times. So then the final answer here will be x in the numerator, x over 2. Let's look at number 7 here. What some students may be tempted to do here is to take the square root of 9, which is 3, then x to the 8 divided by 2, in other words x to the 4, plus the square root of 16, which is 4, times x to the 8 divided by 2, which is 4. This is definitely very wrong. We know that we have this law of exponents, or surds. The nth root of a to the m is a to the m over n. However, we can't apply this law across a plus or a minus. What we need to do instead is to add the terms under the square root, because they are like terms. So 9x to the 8 plus 16x to the 8 is 25x to the 8. And we can write this as the square root of 25 times the square root of x to the 8. Of course, we are using this law. The square root of a times b is the square root of a times the square root of b. And the square root of 25 is 5. And the square root of x to the 8 is x to the 8 divided by 2. In other words, x to the 4. So our answer then is 5x to the 4. Then coming to the last question here, we're going to use this law of surds. The nth root of a times the nth root of b is the nth root of a times b. So applying this law for this expression, we have the cube root of 2 over 9 times the cube root of 4 over 3, and this is the cube root of 2 over 9 times 4 over 3. And of course, this is 8 over 27. Now, we can take the 8 over 27 and raise it to the power of a third. This is using the laws of exponents. Remember that the nth root of a to the m is a to the m over n. So there's a power of 1 here that we don't write. So the cube root of 8 over 27 is 8 over 27 to the power of 1 over 3. And now we can use prime factors of 8 and 27. 8 of course is 2 cubed, and 27 is 3 cubed. This is all to the power of a third. And we multiply the powers. So 2 to the 3 times the third. 3 times the third is 1. So we're left with 2 in the numerator and then 3 in the denominator. So the answer then is 2/3. Let's look at your first answer here. We have to evaluate x squared over 1 plus x, given that x equals 1 plus the square root of 3. So we're going to substitute in 1 plus the square root of 3 wherever we have an x. So 1 plus the square root of 3 all squared in the numerator, and then 1 plus the square root of 3 in the denominator. So we've replaced x with 1 plus the square root of 3. We can square out the numerator. Now just remember that a plus b all squared is a squared, so the first term squared, plus twice the first term times the second term. So twice ab plus the second term squared. So applying this to the expression here, so we can square out the numerator using this rule. The first term squared is 1 squared, which is 1. Then 1 times the second term times 2. So twice the square root of 3 plus the square root of 3 squared. In other words, the second term squared, which is 3. In the denominator, 1 plus 1 is 2. We can add like terms in the numerator. So 1 plus 3 is 4. Now we can take out a common factor of 2 in the numerator. So taking out 2, we're left with 2 plus the square root of 3. Then these factors cancel, and we are left with 2. In the second question here, we have to determine the value of this expression, given that x is 169 and y is equal to 25. So we're going to replace x with 169 and y with 25 in this expression. So x is 169 and y is 25. So in the second set of brackets, it'll be x minus y, so 169 minus 25, all to the half. Now 169 is a perfect square. It's 13 squared, so we have 13 squared all to the half. 25 is a perfect square, so it's 5 squared all to the half. Then in the second set of brackets, 169 minus 25 on a calculator is 144. We can multiply out the powers here. 2 times a half is 1. So we're left with 13 to the 1, or just 13. And here we are left with 5. Then 144 is also a perfect square. It's 12 squared. 13 minus 5 is 8. And here we can multiply out the powers as well. 2 times a half being 1. So we're left with 12 to the 1, or just 12. And then of course 8 minus 12 is negative 4. Let's look at the last question here. It says if 1 over x equals the square root of 5 minus the square root of 3, and 1 over y is the square root of 5 plus the square root of 3, calculate the value of x squared plus y squared without a calculator. So we're given that 1 over x is the square root of 5 minus the square root of 3. And this I'm going to write over 1. Now we have to evaluate x squared plus y squared. So we want x. And we can get x by inverting both sides of the equation. So x over 1, or just x, is 1 over the square root of 5 minus the square root of 3. We do the same for y. So 1 over y is a square root of 5 plus a square root of 3, which we can write as over 1. And then inverting both sides of the equation, y over 1, or just y, is 1 over root 5 plus root 3. Now we work out x squared plus y squared. So x squared is just this squared. So 1 over root 5 minus root 3 all squared. And y squared is just this fraction squared. One squared, of course, is 1. And in squaring out the denominator, it's a first term squared. So root 5 squared, which is 5. Then this sign. Then root 5 times root 3 times 2. So 2 times root 5 times root 3. And then plus the second term squared. Root 3 squared is just 3. And of course here we're using the fact that a plus b all squared is a squared plus 2ab plus b squared. We square out the denominator here in the same way. So the first term squared, this sign, then twice the first term times the second term, then plus the second term squared. We can add like terms in the denominator. 5 plus 3 is 8. And then root 5 times root 3 is root 15. I'm using this rule. Root a times root b is the root of ab, or a times b. Then in the second term here, we can add 5 and 3 to get 8. And then root 5 times root 3, once again, is root 15. So we have two fractions. We want to write it as one fraction. So the LCD will be 8 minus twice root 15 times 8 plus twice root 15. So 8 minus twice root 15 into the LCD, we're left with 8 plus twice root 15 times 1. 8 plus twice root 15 into the LCD, we're left with 8 minus twice root 15 times 1. In the numerator, these two terms can cancel. Then 8 plus 8 is 16 in the numerator. And in the denominator, we have a difference of squares. So we square the first term, minus, and we square the second term. 2 squared is 4, and root 15 squared is just 15. Then we have 64 minus 4 times 15, of course, is 60. And 64 minus 60 is 4. And 16 divided by 4 is 4. We'd like to do an additional example on simplifying surd expressions, and this additional example deals with what we call nested surds. And basically a nested surd is a surd within a surd. So in this example, in part 1, we need to show that the left-hand side here comes to a to the 3/4. So let's have a look at it. Firstly, the left-hand side is a nested surd because we have a surd within a surd. So we have the square root of a times the square root of a. Now, one way to deal with this is to start with the inner surd and get rid of it. And we're going to use this rule of surds that says the nth root of a to the m is a to the m over n. So for the inner surd here, I can write the square root of a as a to the 1 over 2, or a to the half. Now I can use the laws of exponents and add the powers because the bases are the same. So it's 1 plus a half is 1.5, or 3 over 2. And now we can apply this law again to the outer surd. This 3 over 2 here is in the place of m. And of course we have a 2 here which we don't write, which is our n. So this is going to be a to the 3 over 2 divided by 2. And 2 is 2 over 1. So if you have 3 over 2 divided by 2, in other words by 2 over 1, we can multiply the top fraction by the inverse of the bottom fraction. And we can see that this is 3 times 1, which is 3, over 2 times 2, which is 4. So then this comes to a to the 3/4. And we have proved this equation. Let's look at the second question. We are told that if the left-hand side here, this nested surd, equals a to the x, we need to find x. Now the wording is important here. The word now means that we have to use our first result. In other words, the result of the first part of the question. So let's write down. It's a square root of a times the square root of a. And within the square root, there's another square root as well. Now, it's important to note here that we already have the value of this part of the expression from the first part of the question or the example. So we can rewrite it. We have this a here, and the square root of a times the square root of a we saw came to a to the 3/4. So we can replace it with a to the 3 over 4. And now we can add the powers under the square root because the bases are the same. So we have 1 plus 3/4. Now 1 plus 3/4 is 1 3/4. And it's 7 over 4. So under the square root we have a to the 7 over 4. And we can use this rule again. The 7 over 4 being our m and n being 2. So it's going to be a to the 7 over 4 divided by 2, or divided by 2 over 1. And once again we have a fraction over a fraction. We can multiply the numerator by the inverse of the denominator. So we can basically take 7 over 4 and multiply it by 1 over 2. And that's 7 times 1, which is 7. So a to the 7 over 4 times 2, which is 8. So a to the power of 7 over 8. Now, this is equal to a to the x, and hence x must equal 7 over 8, because we have an exponential equation where the bases are the same, and hence the powers must be equal. Let's look at your answers to this additional question. In the first one it says rewrite as a power of x, and we are given this expression which contains nested surds. So let's have a look at it. Once again, it's wise to start with the inner surd. So I'm going to rewrite most of the expression as is. So repeating the outer surd. And the square root of x here, I'm going to write as x to the half. We're also going to get rid of the surd in a denominator by writing it as x to the 7 over 8. Let's continue simplifying. Now, x to the 1 times x to the half is x to the 1.5, or x to the 3 over 2. So here, we're going to get the square root of x to the 3 over 2. And I can get rid of the surd here by dividing 3 over 2 by 2. Then it becomes x to the 3 over 4. So we have x times x to the 3/4. And this is all over x to the 7 over 8. Of course, I could subtract the powers here of these x's, but I'm going to leave it as is for now. So in the denominator, we have x to the 7 over 8. Now, here we're going to get x to the 1 times x to the 3/4, which will give us x to the 1 3/4 when we add the powers. And 1 3/4 is, of course, 7 over 4. So under the square root here, we're going to get x to the 7 over 4. So the square root of x to the 7 over 4. Then getting rid of the last or final or outer surd, we can divide 7 over 4 by 2. So we get x to the 7 over 8. And this nicely cancels with the x to the 7 over 8 in the denominator, and we are left with x as our final answer. Let's look at the second question here. So we have to multiply out this product. Now we're going to use the law or rule of surds that says the nth root of a times the nth root of b equals the nth root of a times b. Both these roots are 5 or fifth roots, so we can apply this law and we can write it as the fifth root of the product of what's under the roots. In other words, the fifth root of the square root of 35 plus root 3 times the square root of 35 minus root 3. And now under the square root we have a difference of squares. So recall that when we have a minus b times a plus b, then this is equal to a squared, the first term squared, minus b squared, the second term squared. So under the square root we have a difference of squares. So we square the first term. The square root of 35 squared is 35. Then we have a minus, and the square root of 3 squared is 3. So we end up with the fifth root of 35 minus 3, of course, is 32. Now, the 32 we can use prime factors for. We know that 32 is 2 to the 5. And now we can use this law of surds, the nth root of a to the m is a to the m over n. So this is going to be 2 to the 5 over 5. In other words, 2 to the 1 or just 2.